Good morning, everybody, again, and I'm sorry about the issue in here with the session. Probably I don't know, I think I clicked on the wrong link or something like that. And again, if you don't see me not here because of probably there is an issue in here, please send me a message right away, because unless you receive a message that somehow the class is canceled, which I don't know when it's going to be, if ever it's going to be at all canceled, unless I'm really, really sick or something big happened, then I'm here, okay? And thank you for one of you guys who sent that message quickly so that we continue this class, okay? Okay, so let's continue now. Let me actually continue. Let me start again, okay? So let me share with you the screen. Okay, so here we are. Okay, so the subject today is on the atoms and the periodic table. It's really the boundary where physics and chemistry meet. This is where basically chemists use this model, basically a periodic table for their applications, which is really how elements interact and so on and so forth. The idea of an atom is an ancient idea, but it was really more a philosophical idea than really based on any kind of observations. So the idea is, for the Greeks, when they were thinking, okay, if you take a piece of rock and you break it into half, you will have a half. You take the half and break it into another half, you're going to get a quarter, and so on and so forth. At some point, we imagine, without any proof, that maybe we reach a point where we cannot divide anymore. So that was the idea of the atom, okay? But it was not until the beginning of the 19th century, toward 1800 something, when the idea of the atom started to get a hold into the scientific community and working on gases, basically ideal gases. And it seems like there is a proportionality between the volume and the amount of matter in here, not because of the density, but the actual numbers of the constituents. So in this case, there is a given ratio of those elements, and that is what is known as Avogadro's number for a mole. And that is when it started to become more and more realistic. Then toward the end of the century, the 19th century, basically there was a discovery of the electron. The electron seems to, first of all, it was a negative charge, we knew that, and it was responsible for electricity and so on and so forth. But the thing with it is, we were able to find its mass and its charge, both of them. Millikan found the charge by itself, but before that, J.J. Thomson basically conducted an experiment and found the ratio of the charge over mass. And since you know the ratio of the charge over mass, and from another experiment, you know the charge, so now you know its mass. So you know exactly that there is a negative charge that exists in there. Of course, that was a problem because you cannot have negative charges, because the atoms, we see them on a regular basis, they are neutral. So there must be another positive charge. So Mr. J.J. Thomson made a model where he said, okay, and this is a point in here, which is somewhere down the road, about the models, trying to make sense of things by proposing ideas, concepts. So he thought, okay, what if the entire atom is like a dough, for example, cookie dough, where you have the chocolate chips are floating around, being basically the positive charge, and the rest of the dough is a negative charge. So that is an idea, the model. So Mr. Rutherford tested that model by throwing alpha particles, which are positively charged particles, we know that come from radioactivity, and throw them on foils made out of gold and silver and gold and silver, and there's another metal. Anyway, he discovered that the atom is mainly empty space, because those positive charges go unimpeded. So those negative charges are far away from the center of the molecule, from the center of the atom. And the center is mainly positive, and it has to be exactly the same number of the charges that are account for the negative charges for each different element. So now it seems like the atom has a center that is positive and an outer shell that is a negative charge, which is the electron. The problem with this model was two reasons. There were a lot of problems with it. One of them is the fact, how could an electron go around a proton in this case without falling onto it? Because both of them, one of them is positive, the other one is negative, so it really should spiral down and fall onto it. So there was a problem in here, so we needed to explain that. And even if somehow you convince me that it's going around in a circular path, it should really lose energy because of radiation. Its charge is being accelerated, so it's going to lose radiate energy all the time and basically fall down. So there was a problem with this model, but there was another issue also with this model too. It seems like the ratio of the charge over the mass for the proton, for the nucleus basically, was not consistent. Sometimes it's for the same element, it's a different values. So it seems like there is a missing particle inside. And sure enough, the hypothesis of the neutron was postulated, and later on the neutron was found. And that's basically the more stable model that we have right now for the atoms. However, there's still those issues of the energy being radiated and all of that that we needed to fix. Mr. Bohr came up with another model. And he said that, look, the electron actually, as it's going around the nucleus, which is positively charged and has some neutral charges, must be doing a harmonic motion in a sense that it's synchronized so that it comes back only with a quantized number of wavelength. It's like standing waves on a string. That's how he basically modeled it. And the quantization, the idea of quantization came before that, before him. So he actually borrowed it from Max Planck, who brought this idea of quantization for the radiation of the black body radiation. Basically, in the black body radiation, what it is we take a piece of iron, it doesn't matter, like this one, for example. It's made out of steel. And you start heating up. So you notice that its color starts to change depending on its temperature. If the temperature is very low, it keeps its color, and then it starts to darken, and then it's going to get into a red color. And then if you keep on heating it, provided it doesn't melt, it's going to change color from red to yellow to basically white color. And it's blue and all of the colors of the spectrum. So we call this an idealized version of this one, the black body radiation. So we wanted to understand what's going on in the black body radiation. And the models that we had before that, or the theory that we had before that, Newton's mechanics, was giving us some nonsense results for it. It was giving us, for the high frequencies, basically radiation, energy that blows up, it goes to infinity, and they called it at that time the ultraviolet, because the ultraviolet was the high energy radiation, the ultraviolet catastrophe, because it doesn't correspond to the actual observations in the lab. So Mr. Planck came up with an idea and said, you know what? Just for the sake of mathematics, he said, I'm going to assume that the wavelength or the frequencies are quantized. And in doing so, he came up with an immaculate explanation for the black body radiation, for this phenomenon. And when people ask him, what does that mean, that quantization of the energy? He said, just take it as mathematical trick just to explain the observation in the laboratory. Obviously, he didn't believe in his own discovery. Okay? And that discovery that he didn't believe in won him the Nobel Prize later on, because Einstein took that same idea from Max Planck and applied it to the photoelectric effect, and it worked beautifully for him too. And that is actually how Mr. Einstein was known too. It was not for his work on relativity or anything like that. That's how he won his Nobel Prize too. And then Niels Bohr also took that same idea from Planck and applied it to the atom, and it gave us very good explanation for what is known at that time, the spectroscopic radiation of the hydrogen atom. So it worked beautifully for the hydrogen atom. So that is really where we were with the quantum stuff. That idea of Niels Bohr unfortunately failed miserably for any other element other than hydrogen. So we really needed to go full quantum, and that is quantum mechanics. Quantum mechanics explains everything. It puts all the entire periodic table into perspective. And you see the entire elements and how they are organized from hydrogen all the way to the super heaviest 118 elements. So this is in a nutshell basically where we were in terms of the entire story for this. Okay, again, it's an ancient idea. It's mainly empty space. As a matter of fact, the distance between the nucleus and the hydrogen compared to the size of the nucleus is about 10,000 times. Very far, very empty space basically. So it's completely empty for the most part. elements heavier than hydrogen, and much of the were produced in the. Okay, initially after the Big Bang, of course, there was hydrogen, and actually a little bit of helium too. Okay, but then in the stars now, where the rest of the elements are being cooked, all of them, including a lot of hydrogen, helium too. Okay. So again, which of the following are incorrect statements about the atoms? Atoms have been around since the beginning of the universe. Around 380,000 years after the Big Bang, the first atoms formed. And then from that point on, they exist for the rest period of 13 point something billion years, 13.8 billion years. So they have existed for every single atom that you can think of. The water that you have or anything that is you made up of has existed since 13.8 billion years ago. So think about it. Other than your conscience, everything existed for billions of years. Okay. Okay. Atoms are mostly empty space. Atoms are perpetually moving, and they have to. If they cannot move, there will be a problem, and quantum mechanics requires that they have to. So the correct answer should be very good. That is the correct answer. Thank you, Lisa. So atoms are manufactured in plants and a human during pregnancy. That is nonsense, okay? Very good. So an element is really, sometimes we use it alternatively to describe an atom. So we use, as long as it's pure of that atom, so that's basically what we have in here, okay? So we use them interchangeably. So when I say the word element, I really mean an atom and vice versa. So the fundamental unit of an element, so that is an atom. So that is basically the point I was making earlier. So this is just terminology at this point. So they make up all of matter around us. Basically, these elements is like a recipe. I mean, how should I say it? The ingredients to make up anything else, okay? So if you look up at yourself, for example, you're made up mainly of carbon, hydrogen, and oxygen, and a little bit of the other elements, nitrogen and other elements in you. Okay? Anything that you can think of is made up of these elements, okay? Or a combination thereof. Now, protons, again, are positively charged, and they sit in the nucleus, and they have the exact same charge as that of the atoms, and they are much, much heavier, much more massive than the electrons, about 1,800 times more massive than the electrons. So when we talk about the mass of the atom, we really are talking about the mass of its nucleus. Because in addition to the proton, there is a neutron, and the neutron has basically the same mass too. Slightly heavier. If you really count the difference between the masses, it's negligible between proton and neutron, but the neutron is slightly more massive than the proton, okay? And protons are the same number of the electrons, both of them. Electrons are identical, repel electrons of neighboring atoms and have electrical repulsion that prevents atoms from closeness. So if you take an atom and you take another atom and bring them closer to one another, their outer shell, the electrons would not allow them to move closer. As a matter of fact, if you push your hand right now, what is preventing your hands to go through one another is the fact the electrons, nothing else. Because it's empty space really between your electron and proton. So protons are not doing anything. They're sitting inside being shielded by the electrons. So what prevents my hands right now to go through one another are the electrons. If I didn't have electrons, my hand will go slide through each other. So that is basically the idea behind it. So the electrons play a major role on a daily basis in our experience in the entire interactions of the universe. The only place where they probably are not important or they become too insignificant is in a neutron star or a black hole. In that case, the gravity will be so much that it brings them closer and smash them into the protons and make neutrons out of them. Okay. So atomic number is the number of protons in each element. It's the same thing as the number of the of electrons. So the atomic number, which is usually referred to as the letter Z, and that is what you see in the periodic table, okay? So that refers to how many protons or electrons you have in an element. Neutrons, they're with the protons, and that is the one that makes the difference between one element and another of the same element. So you could have, for example, iron, and you could have another iron. Both of them are iron. Both of them do the same chemistry. But one of them is a little bit more massive than the other one. And the difference comes into, in this case, the neutrons. And that is really two different, what we call them, isotopes. So neutrons play a role, not just in terms of the mass, but they play a role also in, and we're going to talk about this one, in gluing the neutron together. I mean, the nucleus together. So if you have a nucleus made up of a proton and another proton, so in here you have two positive charges. If you bring them, separate them slightly, they will fly away from each other because both of them are positive. If you bring them closer to then a certain minimum distance, they will attract one another. But it's really not that strong, the attraction in here. The attraction is a nuclear force. So what you do in this case, you bring a neutral charge, and the neutral charge in this case is, which is a neutron, and this, they will attract this, guys. They will attract this one. There is an attraction in here. There is an attraction in here. And there is an attraction even in here between these two protons. So it strengthens the element, the nucleus. So this is the nucleus of the helium, actually. That's made up of two protons and two neutrons, okay? In the case of hydrogen, you only have a proton. So you really don't need anything else to hold it together. It's by itself. But in the case of helium, for example, you have two protons. And because both of them positively charged, they tend to repel one another, except when they are closer than a certain distance. In that case, they will attract, but the attraction is actually still impeded by the fact that you have positive charge trying to repel one another. So you need protons to help one another to get them to stay together, okay, in the nucleus. So the neutrons, they play a role actually in the stability of the atom because of the fact that they keep the proton together. So isotopes, I refer to them, I refer to atoms of the same element that contain the same number of protons, but different number of neutrons. So they have the same chemistry, they have the same Z. They have the same number of electrons. An isotope and an isotope are the same, basically, chemistry, but they have different mass number. The mass number A is different. Why? Because you have different neutrons in them. One of them has more neutrons than the other, okay? Differ only in the number in mass, not in electric charge. Therefore, isotopes share many characteristics, especially chemical characteristics. So the total number of neutrons in an isotope equals to the mass number minus the atomic number. It's A minus Z. So how many neutrons? N is the number, the mass number minus the number of protons, which is Z, okay? So if you're inclined to mathematics, this is the formula that we need to use. So the total mass of the atoms, protons, neutrons, and electrons listed in the periodic table as units. So this is the atomic mass. So when you look at the periodic table, it lists Z and it lists A too. And A is actually the sum of the mass of the proton, neutron, and electron. And when you add up these masses, actually you will find usually there is a tiny fraction missing, and that tiny fraction missing, which is negligible, is really what needs to exist to hold the atom together, okay, to keep it stable. Okay, so this is basically, if you see an A there, for example, oxygen is 16, you have to multiply 16 by this number to get how many grams that is, or this number to have how many grams that is. Kilograms, that is. So the atomic number of an element matches, did I multiply? I'm sorry, it's the exact number, okay, 16 grams per mole, okay? The atomic number of an element matches the number of, so this is Z, the atomic number is Z. The number of protons in the nucleus, that's correct. The number of electrons, that's correct. Either one or both. So the correct answer is C, actually, too. Okay. So a nucleus with an atomic number 44, that means it has 44 protons. If you don't like this word, you can say it has 44 electrons. It's the same thing. When it's neutral, one neutral. If it's not neutral, it may have one or more electrons or one or less electrons. So this is when it's neutral, it's the same number of electrons and protons. And a mass number of 100. That means I have to add a number in here to make it to 100. So again, the number of neutrons is equal to the mass number, which is in this case 100, minus the number of protons, which is 44. So the answer is 100 minus 44, and the correct answer is very good. Yeah. So it must be B. So the periodic table is really the listing of all of the elements with a logic in it. It's not something that you need to memorize, and it's something to be basically understood, okay? So chemists use it extensively, and you cannot walk in any chemistry lab without seeing it. So this is basically what the periodic table look like, okay? Usually it's color-coded, okay? And the color coding has a meaning in here. All of these materials that you see them in orange in here, it is what is known as metals. Basically, they have the ability to give in one electron or more, okay? Or the elements in here on the left, on the right, I'm sorry, that you see with this pink color, they have the ability to capture one or more electrons, okay? So these are the opposites of the metals. So these are called metals, these are called non-metals. These ones, they cannot make up their minds, okay, the green ones. They are basically sometimes behave like metals, sometimes behave like non-metals. So they are transitionary, I'm sorry. So these elements in here, especially these two, silicon in here and germanium, plus the arsenic in here and gallium, play a major role in semiconductors. Because metals are conductors in general, because they have free electrons to move around. These guys, they are the opposite, okay? Unless they are in some sort of a ionic structure, then they become good conductors. So this is basically how this thing is organized. Look at the hydrogen in here. Hydrogen has both colors. Hydrogen can behave like both, okay? Sometimes it does, actually, as a matter of fact, it's by itself. You have actually three types of groups in here. You have the metals, you have the non-metals, and you have hydrogen by itself, because hydrogen can do other things that anything else cannot do. Okay, it can actually force other materials, basically other atoms, to fuse together and make a new, not fuse, I mean make a new molecule. So it's part of a bonding structure for other molecules, okay, especially in organic chemistry. So that is really how the periodic is organized. All of these elements in here, they have an excess of one electron. They can give one electron. So they have the same chemistry. I mean, skip the hydrogen as I was talking about. Lithium, sodium, potassium, all of these elements, they can give one electron. This ones, beryllium, manganese, calcium, and all of these elements, they can give you two. Okay, so when you have them in a chemical reaction, they can give two, I mean, a chemical bonding, they can give two. These elements, they have a different behavior. Okay, they involve a different shell. Okay, they involve the D shell, actually, the D subshell, D shell in there. This ones involve the P shell. And you start with 1, 2, 3, 4, 5, and this is full. So these elements in here, they are inert. They don't do anything in chemistry. They don't react with anybody. They don't, most of the times, they're basically, they don't have any kind of chemical reactions. And they're inert. That's what the word means, basically. It's like as if they're called the noble gases, okay? At least with the exception of helium, these are the noble gases: neon, argon, krypton, and xenon, okay? So these are the noble gases. These are the halogens. They can take one electron. Fluorine and chlorine are the two main ones. And combine, for example, sodium with chlorine, that is what salt is. So this can give one electron. This can take one electron, and they do that. The the outer electron in here from the sodium is given to the chlorine, and now you have salt that is formed. Actually, they can form salt with other elements in here in the periodic table. Anyway, so this is in a nutshell how the periodic table is organized. The elements are highly organized within the periodic table. Each vertical line is called a group. So these are groups. So this is the alkali group, okay? And you can call them the lithium group, okay? That's how I actually like to call them myself. The alkali group. This is the alkaline earth metals. This, the beryllium group in here, they can do too. And then the rest of them, they really don't have any name in here. So this is the scandium, titanium group, palladium group, krypton, iron group. So there is a bunch of groups in here. And then you have in here the boron group, the carbon group, which is this semiconductors in here. And then you have the nitrogen group, the oxygen group, and the oxygen group have a name that I forgot. It's kind of chalcogens. Yeah, that's what they're called in chemistry, chalcogens. And then you have the fluorine group or the halogens, and then you have the noble gases. So they have similar chemistry. That's why they are grouped in this way. On this side, you have the periods. So you have period, you have the groups on top and you have the periods in the bottom in here. This is period 1, 2, 3, and so on and so forth. So there is a highly organized structure in here, okay? These guys that you see them with this arrow in here, they're supposed to be in here. You're supposed to push them in here. So this periodic table really looks like this like a ladder, and then it breaks in here too, to a very long one, and then it rises again to go back into here. So this is really supposed to be stretched this long. But we don't want to stretch it that long because these elements in here are supposed to be sitting in there. That's why we have them in there. So the periodic table only have 1, 2, 3, 4, 5, 6, 7 periods, okay? These 2, they're supposed to be here, and the 6th and the 7th period. Make sense? Okay. So the horizontal row is called the period, and this is how they are now, okay? So this is the 6th and the 7th subset of this period in here, okay? So this is how we understand it. Again, you're not supposed to memorize any of these things. These numbers that you see on the periodic table, let me look at them in here too. These numbers in here, 1, 3, 11, 12, 25, 108, those are the Z number. This is the atomic number, okay, for each and every one of those elements. In other words, how many protons do you have and how many outer electrons when it's neutral they have, okay? Take fluorine, for example, it has 9. It needs 1 more to become full, to become 10. These are the ones that are full capacity, okay? Because this periodic table is not listing the mass number, usually you have it in here, but because you have different isotopes, usually give you the average based on the weighted average of the mass number in this case, okay? Again, in terms of size, because now as you move this way, more and more protons are inside. Look at it again in here. You have 1 proton, now you have 2 protons. You have 3 protons, 4, 5, 6, 7, all the way to 10. Since you have more and more protons as you move along this way, they're dragging more and more the electrons towards them. So the size shrinks when you move this way. But it grows also when you come on this side too, because you have more now electrons. So the size of the atom grows as you come down on the periods, but it shrinks when you move this side to the groups. Make sense? Okay. So this is the physical size. It's really not usually as important. One of the questions that is asked, for example, is this how to compare them. Okay, here is the big names, okay, that are used, and it's a good idea to remember them more or less, okay, so that you know what they're talking about. So if there is a word metals associated to it, you know that you are on the left, okay? If the word metal is not associated with it, you are on the right. These are the noble gases. They don't participate in any chemistry. Halogens, they're opposite to alkali, okay? And then you have the chalcogens. They're opposite to the alkaline earth metals. And then you have the transition metals that are in the middle, okay? These guys have no name yet, okay? But again, if you just want to stick to the naming, you can just go with the lithium group, the beryllium group, and then all the way to the boron group, carbon group, nitrogen group, oxygen group, and then the fluorine group, okay? And now the noble gases, okay? Again, this is the inner transition metals. Those are the ones that go inside. Now, if you want to compare sizes, obviously lithium is greater than fluorine in this case, because you'll have more protons in the fluorine than in the lithium, so attract the shell in. And in this case, because you move between sulfur and arsenic on this side, because now you have more electrons, so there's the arsenic now should be bigger than the sulfur. So physical models replicate the object at a convenient scale. Okay, it's very hard to do that. As a matter of fact, the atom was not pictured. It was very hard to take a picture of it with regular light because the wavelength of light is very it's very long compared to the size of the atom. So we cannot really use light to see the atom. So we had to use really an electron microscope to see it, okay? So that's the idea behind it. Physical model replicates the object at a convenient scale. Conceptual model describe the model. That describes the system. So we usually really use the conceptual model in this case, okay? So spectroscopy is an instrument that is basically take light that you can shine it, for example, on a diffraction grating like this one. When light goes through it, it's going to be broken down into different components. When different spectra on it, depending on the wavelength, it's broken. So we use that now to analyze and study what do we have, what kind of element do we have. It was actually shown that toward the beginning of the 19th century, that different elements have specific frequencies that correspond in their analysis. It was Johann Balmer who came up with an expression, at least for the hydrogen atom, that there is a number in there in the formula that depends on 1 over n squared. So depending on when n is, n equals to 1, 2, 3, and 4. So there was a mathematical relationship in there, and Rydberg later on basically noticed that, okay, I can add up 2 frequencies and I come up with another one. So there is a discrete in here, discreteness. I mean, there is like, they come up in integers, values of multiples of one another, or you can sum up things. And it seems like there is that mathematical relationship, hidden structure in it. If you look, for example, at different elements, they have different spectral lines. If you see the spectrum alone in your studies, then you know you have strontium inside. If you see this spectrum, you know you have potassium. If you see this spectrum, barium. So each and every one of them has its own signature, and that is a unique signature, number 1. Number 2, there is another thing in here that is not stated, but you guys probably have suspected already. This is the visible light. What happened in here for frequencies that are a lot longer than the red? If I have a detector for the infrared, I should see actually more and more stuff in here, possibly. If I have detector in here in the ultraviolet, I could see probably an extension on this side. And the same thing in here, this side and that side, and so on and so forth. So if better detectors, for example, for the high frequencies and low frequencies, we could see more. And each and every one of those transitions seems to be indicative of a specific atom. Not only that, but look at the lines. They are specifically sharp line that repeat all and all and all. And the distance between them, that is what Johann Rydberg came up with, that relationship in here. It seems like there is a relationship between these distances in here, between the 2 different frequencies, okay? And the explanation for it then is that, look, each atom has an energy level, and each energy level is separated, at least in terms of the frequency, with a specific value. So when the atom is excited to the next level, it can only emit those frequencies that are consistent with that element. In other words, if I have an atom, this is its energy level 1. This is its energy level 2. This is its energy level 3. This is its energy level 4, for example. Then I can only have a transition between this level and this level, or this level and that level, or this level and that level, or this and that, okay? Or finally this one. For example, I only took 4 in here. So those are what I was looking at. This is the high frequency. This is probably the next one in frequency because the gap is very large in here. This is the next gap. This is the third gap. So this will be toward the blue or the violet actually. And this ones will probably be, this one probably under the infrared or red and so on and so forth. So that's what I was looking at, okay? Different element will have probably different levels. This one probably the next element has in here and maybe here and here and there. So now this signature for specific element, this one is a different element altogether, okay? So because the energy levels, first of all, they're not the same for all elements. They're different for an element and element, depending on how many protons you have inside and how many electrons you have, and how many other configurations that you can have in that element, number one. Number two, even in that element, the energy level, the separation between them is different for that element than the next element. So it's not like you take that, that element and move all of the energy levels up or down. It's actually the gaps between them are different. And that is what we were looking at. Each and every one of those elements has its own specific signature. So one spectral line does not make the whole story. So if I just see one frequency, it does not mean much because potentially there is another element whose transition between some level to another level could correspond to that level, okay? Albeit this is very rare, but it's possible. But if I take the entire story, then I know for a fact that this is it. It's like fingerprints, really. When you have, each person has his or her own fingerprints, that is exactly what's going on with the spectral lines. So that is what allowed us really to understand what's going on in here, okay? So each spectral line in an atomic spectrum represents specific frequency of light emitted by an element, one of the many colors of an element, a pattern characteristic of an element, no, okay? So each line is actually a specific frequency emitted by that element, okay? So a hydrogen spectrum consists of many spectral lines. How can this be explained? Because one electron, so basically we have only one proton and one electron. So why do we see many spectral lines? Because that electron could be in this energy level. I mean, I represent it in terms of distance, in terms of physical size, actually. And that energy, so this is the energy representation. So the reason why I'm seeing different lines in here, because one hydrogen atom could be excited in here. All of them probably are excited in here. They were raised to the same temperature. Another one could transition in here, and then from here to here, or from here to here, and then from there to here, or from here to here, and depending basically on it. That's why I'm looking at different lines in the spectrum. So it's the same electron, but from one atom to the next, doing different transitions, okay? When an atom is excited, its electrons are boosted to higher energy levels. That's what that means, okay? So an atom that is not excited, the electron sits at the ground state. This is called the ground state. Then when you excite it, depending on how much energy you put in it, the electron or the entire atom is boosted now to a higher energy level, okay? If the excitation is so high, if the energy is so big, then you can ionize it. Actually, the electron can leave completely the atom, and the atom becomes positively charged. In this case, it's an ionization, okay? So for example, to talk about the hydrogen atom, to do that, to ionize it, you need 13.6 electron volt, because the electron volt is a unit for energy, by the way. Because it's bound by that much energy to the proton in the ground state. So if you want to kick it out, you have to basically give it that much energy, and that's a lot of energy, by the way. So if you can pull the electron from the atom, you need this much energy. Max Planck, I already talked about this story, hypothesized warm bodies emit radiation energy in discrete bundles called quanta. Energy in each energy bundle is proportional to the frequency. As a matter of fact, he wrote this expression: E equals to H frequency. H times the frequency. Okay, this is the energy. Where what is H? It's just a constant. Okay. In other words, the energy and the frequency are the same thing within that constant. So at the end, that constant, now people call it Planck's constant. Okay, this is really the first assumption for the quantization. Einstein, actually, when people were studying the photoelectric effect, basically, if you shine light on a metal, electrons are ejected if the frequency above a certain threshold. If the frequency is below that threshold, no, nothing. You cannot see anything. Okay, there is no electron that is emitted. So this was known as the photoelectric effect. So Mr. Einstein made up took this argument, and he said that frequency is energy. If this photons has specific energy, they can overcome the so-called work function in here, which is how much the electrons are held into the metal and can eject it. And that's how you have the photocells above your household. Okay, so that is the principle behind it. I know we're accustomed to having discussion topics in here, and I want you really to have an item in here. And since this is a big deal, really, okay, I want you to reflect on the work of Mr. Planck, okay, and I want you to check his background really on this topic. Without getting into a lot of theory, just basically a couple of sentences, 2 sentences or more. Okay? Because this is really the main thing that makes the difference between classical mechanics and quantum mechanics. And quantum mechanics is really that can explain everything in here that we need, okay? It explains everything that we have in here. And it is behind the revolution that the reason why you have cell phones and computers and electronics and everything else, and all of that advancements that we have nowadays is because of the development in quantum mechanics, because of these things. He himself, as I was saying, did not really think that it was not justified in a sense. He didn't know how to justify it, but he was able to explain this how warm bodies basically radiate energy beautifully. As a matter of fact, this is how the radiation of the black body experimentally was shown before his work. So this is the intensity of the energy, basically, depending on the frequency. So this is the lambda, which is the wavelength. And this is the distribution, okay? Different wavelengths, they come with different intensities. So this is the intensity, if you wish, okay? Depending on the temperature, this is for a given temperature of an object. It has to be warm enough to have measurements in here of significant things. People before him, actually Rayleigh, when he tried to explain this, when he found that the energy blows up and goes to infinity for high frequencies, meaning short wavelength. This is short wavelength. So this was called at that time, look, there is a problem for ultraviolet radiation. Black body should emit an infinite amount of energy, basically, which is nonsense. So they called it the UV catastrophe, because no theory could explain it. Catastrophe. Okay, no theory could explain it. So Planck, when he did this hypothesis, the theory he came up with was an immaculate reproduction of the experiment. So he knew that he had the correct model. but he didn't know how to justify it. Okay, he didn't know how to explain it. Now he became famous for it. If you go to Germany, there is a huge institute in Germany called Max Planck Institute, and actually he was basically the father of quantum mechanics as we know it today, because Einstein took his work, Niels Bohr took his work, a lot of people, and later on quantum mechanics came up based on this whole thing in there. So this is basically in a nutshell what this expression is saying. The energy is proportional to the frequency. So this symbol in here means proportional. Okay, not equal, proportional. Comes in proportion. The higher the frequency, the higher the energy. The lower the frequency, the lower the energy. Okay, that's basically what that is. And it's made up of tiny particles now, since it comes up with a different frequency. Each one of them has a momentum. This is actually the idea of momentum was due to Mr. Einstein, who took that idea and introduced the momentum in there. For this is like a collision of a particle, which Einstein called it a photon, actually. So this is how the idea of the photon came out to be. When it hits the electron, that collision will kick out the electron out of its path. So this is basically the idea that emerged from there. That light is not a wave. I mean, we did the chapter before about light when we said light is a wave. In this phenomenon, light is not behaving like a wave. Light is like a particle, like a tennis ball, for example, okay? So light is a particle called photon, okay? Light is a stream of particles. Light can be described both in models. So it's, I mean, if you go back to light, the way that we were experimenting interference and everything else, so it's really a wave. And now it is really a particle. So which is it? Both. Okay. So it sounds contradictory, but that's exactly how quantum mechanics is in terms of describing things. Okay. So light is both. Okay. So the symbol in here, F, stands for the frequency emitted by, and E stands for the energy of the photon. Okay. Which of this has the greatest energy per photon? It must be the blue light. Okay, blue is on this side, the high frequency, short wavelengths. So this is blue. On the opposite of that, there is the red. Red is low frequency, long wavelength. And you are in energy this way. So this is higher and higher energies. Okay, UV is here, X-ray is here, gamma rays are here. This is the visible spectrum. Infrared is here, radio waves is here. And actually there is a microwave in here too. Okay, so this is the spectrum in terms of energies. Which of these photons has smallest energy? Infrared, visible, ultraviolet, must be infrared. If you go back into the model here, this is where the infrared is. So the infrared is actually less than the visible light, which is less than the UV, okay? So Niels Bohr came up with an explanation for the atom to some extent with a new model. And in his model, because people could not, there were difficulty with the model that was coming up together at that point, in that they have, that is depending on the Rutherford experiment, and Rutherford experiment said that it's like a planets basically going around the sun, but that's not correct because we know that planets are neutral charged, so they don't emit radiation, but these particles are actually positively charged and negatively charged, so they must emit radiation while they're going in circular paths. So this model is not correct. So he's hypothesized that they're actually like standing waves on a string, basically. So the only way for this ones to be standing waves if that the wavelength is multiple integers of this length. Okay. So, and that then, except that they're in a circular path. So I will try to draw a circle in here. And then this is the starting point. This is more or less one wavelength. This is another wavelength. So this is, oops, I did not do it correctly, okay. If you do it this way, it's a standing wave, okay? Where the angular momentum is quantized in the same fashion that Mr. Planck introduced the quantization. And from there, he found an immaculate, impeccable spectrum of the hydrogen atom, with the exception that there were some problems with it on a smaller scale. When you go into very closely from it with high precision devices, you will find that there is a splitting in the spectral lines that he could not explain with this theory. Other than that, at least for the hydrogen atom, it works. Only for the hydrogen atom, okay? If you try it with helium, it doesn't work, or any other element doesn't work. So this idea of Mr. Niels Bohr actually was a good starting point, but not the whole picture, okay? However, when an electron energy level drops closer to the nucleus, emits a photon. Bohr reasoned that there must be a number of distinct energy levels, has a principal number n, and each energy level, he at the end came up with this formula. Each energy level has this value, where n is equal to 1, 2, 3, and so on and so forth. The negative number just to indicate that it's tied to it. It's not free to move around. The negative number just an interaction. 13.6, that is an electron volt, and n is an integer. So this is what he found. And this describes exactly Balmer's basically formula and explains exactly Rydberg's basically difference between frequencies. So this, his job was tremendous, Mr. Bohr. I mean, he explained a lot about the spectrum. There was some discrepancies with it though, but people knew that they were on the right track. This is actually the right way to go, okay? Unfortunately, they couldn't modify it for the other atoms, number one. And number two, there was those annoying broadening of the lines that could not be explained by the spectrum, okay? And that was an issue. That was a big issue, okay? So that's where quantum mechanics had to really be invented. And of course, the quantization in here where n is an integer, so it's asking you which one is a quantum number. Obviously, 2, it would be a quantum number. Like I said, n is equal to 1, 2, 3, and so on and so forth. So these are not quantum numbers in that sense, okay? These are not integers. Bohr's model explains why atoms do not collapse. So he has a stable atom now, at least for the hydrogen atom. Electrons can lose specific amounts of energy, equivalent transition between levels. An atom reaches the lowest energy level called the ground state, where the electron can't lose more energy. So you cannot go below n equal to 1. Because if you go back to the formula n equal to 1, did I write it? I wrote it in here. If you put n equal to 0, for example, that is going to be dividing by 0, and that's an infinite amount. So there is no other number. So that is where the ground state is. So there is actually very good, it's a very good model, okay? It's a very sound model and explains a lot of these things for the hydrogen atom. Okay, again. The planetary model before it did not work because again, photons are emitted and as electrons move around, so that's not going to be a stable atom anyway, so we discarded that. Now we came up with another explanation somehow that the electron, and this is due to Mr. de Broglie in 1922, in his thesis for a PhD degree, he suggested that, look, since the photon can be a particle and in the wave, and there is that duality, why not for the electron? Electron is a particle, yes. Can it have a wave? That hypothesis solved the problems, all of them. That really nailed a lot of the issues there, okay? Quantum mechanics developed immediately after that. Mr. Schrödinger came up with an equation to satisfy the condition of Mr. de Broglie. And then at the end, we came up with a new branch of science called quantum mechanics, as I was saying. This is basically the thing I was trying to draw earlier. This is a Niels Bohr model still, okay? Now this is what we ended up with, actually, the shell structure. That if you go back into the periodic table now with the shell structure, it's beautifully understood because this is the S shell, 1s shell, okay? This is the 2s shell, okay? This is actually the boron. You have the 2s and the p shell in them. 2s, actually the 2p. Let's write the p in here by itself outside, because I'm just writing the outside in here. I'm not concerned about the inner one. There is actually the 1s shell in here that explains that. So this is the 1s shell, similar to this one for the helium. Actually, this one is like the helium with the exception that now it only has one of them. This is fully counted for. That's why this is neutral. Inert, I'm sorry. All of them are neutral, okay? This is the 1s shell plus an electron that moves to the 2s shell. So this 2s shell is missing one electron. And here it has two electrons, the 2s shell. Now we're moving to the boron in this case because we're fully equipped with the 2s. So again, we have the, I think there is an issue in here with the representation. The energy level slightly above this one. But again, the 2p1 cell and so on and so forth until we get the p cell also full, okay? And then the shell structure explains beautifully the periodic table, okay? And that is what we have nowadays as an explanation for the periodic table, okay? So chemists use the so-called SPDF shells, depending on n. The n is the number I was talking about earlier. If n is equal to 1, then you only have one level in this case, which is the 1s. When n is equal to 2, then you have two possibilities, either the 1s or the 2s and the 2p comes into play. Okay? No, the 1s from the previous level. For n equals to 3, then you still have the 1s, the 2s, the 2p, but now you have the 3s, the 3p, and the 3d, and so on and so forth, okay? And then comes into F. If you follow this pattern, okay, you don't really need to know this thing. I know your class is not going to get into much deep of these things, but if you follow this pattern, you have the entire periodic table explained with the shell structure, okay? So I'm going to see you guys on Thursday. Hopefully I would not make the same mistake with the link. And if there is, please, if you don't see me 5 minutes before the class, 10 minutes before the class, even 15 minutes before the class, and you are in, please send me a message. Hey, we're here. Okay. Thank you.